Hello, everybody.
What's up?
Welcome back to the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray. And for the first time ever, we are doing a live podcast. I think this is really exciting. Hopefully, we'll be able to do more of these. But as you know, of quarantine situation and online schooling, we're not in the same city. So it's going to be a little hard, but hopefully more we can do of this, the better.
Yeah, so if you're listening on Spotify or Apple or anything that doesn't have video, make sure to check out the YouTube video because we're going to be posting the recording of us talking live in person on YouTube. So yeah, very exciting.
That's going to be pretty cool.
Yeah, so I'm visiting Toronto right now. I think we're going to record at least one more in person.
It's coming up. Just stay tuned.
Very excited for that. Okay.
So, I have to say something about the episode that dropped today, though. I think we both do. There was an episode dropped today, the Black Pen, Red Pen episode. This was like the big one that we were talking about, the big interviewee. This was Steve Chow, part of the huge YouTube channel, Black Pen, Red Pen. And I think that interview was awesome. Yeah. I think that interview was awesome.
That interview was awesome. So, if you haven't checked that out, definitely check it out.
Definitely check it out.
Our biggest interview to date.
Yep.
So awesome.
That's true.
And also one more thing I wanted to say is that we're gonna post an unedited version of the podcast on YouTube. So the live version, we're not gonna edit anything out. You know, usually I edit out like coughs or like anything that like if I like mispronounce a word and then like correct myself, I'll take out the first part so it just sounds like normal. But yeah, so the unedited version is gonna be on YouTube if you're watching right now, and then just like the regular podcast is going to be posted on Spotify and everywhere else.
That's awesome.
So yes, getting into today's topic.
Today's topic is interesting, actually.
Yeah, we're going to talk about numbers, all types of numbers. So we're going to go through, the simplest ones up to, the most recent. I'm not going to spoil it. You guys probably already know.
I think you were going to say the word, but you can't say the word because it's associated with what it's called. I know what you're talking about.
So we'll just start with...
let's just start with the most basic.
The most basic ones. And we talked about this also on alien math. We kind of described what these numbers were and why they're kind of so elementary. And it's kind of like... It makes sense, right? Why they're
pretty important.
Why they're...
and then they're pretty essential in the universe.
Right.
And all these different types of numbers.
And it's very obvious. So
yeah.
So the first kind of numbers are the natural numbers.
The most basic.
So these are just positive integers. When you're counting, 1, 2, 3.
Things you can see. Things you can see.
All the way up to infinity, right? It doesn't end. But it's just the whole numbers. And funny thing about the whole numbers is that 0... right? 0 wasn't actually a number up until a certain point.
Yep. So, interesting fact. So, natural numbers, I believe, were like, I think the first type of numbers to be invented. It makes sense if it was in about 300 BC. Now, 0 was invented around like 4 AD, which is like 300 years later, right? So, basically, the origination of natural numbers for the first 300 years was just... the numbers, the things that we can see. We can see one chair, we can see one laptop, or probably not laptops in 300 BC, but, we can see 1, 2, 3 of certain things. We can't see -5 of anything, or 0 of anything, right?
But turns out 0 is pretty important.
Very important.
And so when you talk about the natural numbers, sometimes people will refer to just 1 and up, and sometimes you'll talk about 0 included in that set. And so I think by convention today, when you say the natural numbers, that implies that 0 is a part of it.
I think we just regard 0 as a part of it.
If you want to talk about 0 not included, you would write like n plus.
N plus.
Right? So that just means the natural numbers that are positive, which just excludes 0. So
that is usually what we're talking about, but like because of how useful 0 is, we just include it in the natural numbers because it's very useful number.
Yeah. So
even though it's actually quite useless, we can have a whole podcast on 0 though. I think we can have a whole podcast on 0.
Why do you say? It's
okay,
useless?
So like in essence, what 0 does is it takes anything and it makes it zero. Oh, well, I'm sorry. It takes anything and it makes it zero. So it doesn't, I don't really see how it's very useful, but it's still a very useful number to have. It's very useful in a lot of cases where decimals and, 0.00, 005, stuff like that.
What about this?
Yeah.
You say zero is not important. What about when you're taking limits as x goes to 0?
That's important. That is very important.
Pretty important.
If you think about it, graphs were probably not even conceived of without an x equals 0. So there was no starting point because there was no 0 at that point.
Because graphs were invented by what's his name, Cartier, I think, something it's in a Cartesian graph.
Cartesian graph. Right? Oh, true. When was that invented?
Because Cartesian it's named after the guy who invented it, and that was pretty recent.
The Cartesian plane was invented in the 17th century.
There you go.
That is pretty recent.
So,
actually, 1600s.
So back when they were using natural numbers as
obviously no graphs.
Yeah, they weren't talking about
not
graphs.
even close. Nowhere near.
A natural extension to the natural numbers, which this comes, later on in the history of mathematics, and that's where we talk about integers, a set of integers, and that's denoted by a z, a z with 2 bars in it. So the only difference is that we're considering negative numbers now.
Yeah.
Which, of course, every time we talk about a more complex set of numbers, it comes with its benefits, of course, and its
cons, and it's.
I don't know about cons.
Not cons. Sorry, confuse. Okay, when you invent a new number system, there's a lot of confusion, not cons.
Yeah, in the beginning.
I meant to say confusion around the whole system,
and
because the idea of negative numbers when things weren't even thought of as negative.
Right.
How do you,
the reason why this was so controversial was because, let's say a mathematician would say, okay, -2. Somebody, let's say a farmer, would be like, hey, -2 doesn't mean anything, right? I can't sell you -2 corns. That doesn't make any sense. And so people wouldn't really understand the concept of something being not there.
But interestingly, the first ever, or at least thought of recorded, not really recorded, but again, what we can date back to use of integers where negative numbers were used actually could make sense to the common person. Where this was used in about 600 AD by an Indian mathematician, where he represented positive numbers to mean assets that he owned and negative numbers to mean debt.
Yeah.
So I guess it would make sense if you put it that way.
Yeah.
But if you're selling -2 corn, that just makes no sense.
It only makes sense in kind of a theoretical.
Yeah, in a theoretical idea. Because debt isn't a real thing. You haven't. Yeah.
It's not a physical thing. It's not tangible. So that's just an example of where you would use negative numbers, and also when you're subtracting things, that's kind of a real process, right? If you have a set of 10 objects and I give you 2, technically, yes, I'm doing 10 plus -2. So technically, when I'm giving you 2,
you're not really, you're adding the negative.
That's kind of the physical representation of the negative number.
I think that's why adding and subtracting is also. I think we can also talk a little bit because we're talking about numbers. We can also talk about what's the thing that bind them? Positive, negative, multiply. What are they called?
Operations.
Operators. Yeah. So I think those are also kind of cool, especially the plus and minus operator. In the fact that you can, I think we did. I think we did.
Yeah.
Where you can always add a negative, subtract a pot. It always works out with the add and negative, and even with multiplication and division, it's just so seamless. You always multiply something divided by 1, or you can just just divide it by 1 divided by that number. So it's just I don't know. I think the operators make a lot of sense, and it's very satisfying to see them work at times.
Talking about operators, think about this. As soon as you invent division, what else do you invent? Rational numbers.
Oh, rational numbers.
Right,
are we starting it? Okay, one thing I have to say about integers though.
Okay.
So integers, as I said, was thought of to be invented pretty long time ago, 640 AD. But then in Europe, it was starting to be used more in 1563, when basically this guy was doing an experiment with elephants and bunnies, and after a few weeks he saw that the bunnies had breeded. So he was trying to make up a formula to try. So he made up addition, subtraction, multiplication, and division through that experiment. Obviously, this was just invented in Europe for him. It probably was used in various other places when he didn't know it. But so he took 15 years to make up a multiplication division system. Wow. I don't actually know if he was successful. I think he probably was. After 15 years.
I mean, the fact that this experiment today is probably
it probably is. It was successful.
So yeah, going into rational numbers
rational
now,
numbers
denoted by the R, right? No,
that's not true. That's Q. That's Q.
It's a Q.
Yeah, we're tripping. That's
so the Q is a rational number. A rational number can be described by, right, if you have an integer A and an integer B, the rational number is just going to be A divided by B. And so this encompasses all of the numbers that we've previously talked about, because if you take B to be 1, then you just have all of the integers, right? Because A can range from negative infinity to positive infinity. So it encompasses all of the integers, but now you can go in between integers, because if we take, 1/2, now you're falling in between two numbers that previously you could only be on the whole numbers themselves.
But there are certain numbers in the rational numbers that don't work.
We're not there yet.
Oh, we're not there yet? We're not there yet.
Okay.
I thought that was a transition.
So let's talk about what's the advantage of having rational numbers.
Okay.
Right? So now we can do, right, halves, quarters, we can
5.8.
Exactly. We have decimals. Now we have infinitely more numbers, right?
Decimals.
So before we had two types of infinity, right? We had positive infinity and negative infinity. And
what was infinity? Was the concept of infinity invented at that time?
I'm not sure, to be honest.
I don't know, actually. I mean, I don't think infinity was invented when they thought of natural. Like, I don't think people actually thought, how high can you go with numbers?
I think conceptually infinity was an idea.
No, conceptually it's always like, how big? Like, I have one chair. How many chairs can I get? Like, conceptually it's an idea, kind of thing.
It's funny how we always take like objects from...
It's right here. I'm sorry. There's a chair right here. You guys can see it.
Two pieces of paper. But no, I was gonna say. Right. Talking about infinities. You got positive infinity with in the integers. You can go one way. You can go the other way. But now, you don't have to look very far to find infinity when you're dealing with rational numbers. If you just look at between 0 and 1, you can find an infinite amount of decimal numbers in between those two integers, and then you could find the same thing in between every single integer. So you just get wildly
because because it can be 9, it can be 99, it can be 999, it can be 9999, it can keep going, right? So there's literally infinite. But then, there's the really cool thing that we can talk about where we prove if 0.999 recurring equals 1.
Yeah, so that's done with series, basically. Yeah. If you find well, I guess we were just taught this.
Yeah.
But, so there's a formula for when you're doing a geometric series. And so when you're adding, 1/10?
No, isn't it 9/10 plus 9?
It's 1 minus the sum of 1/10 plus 1/100 plus 1/... Because you're taking off...
No, it's...
Oh, no, that's
no. It's 9/10 plus 9/100 plus 9/1000 plus 9
right. But you factor out the 9.
Exactly. Then you factor that out. And then if you do the series, if you take the infinite series, then you get it equaling 1, which is pretty cool.
Yeah.
So
I don't know if that was confusing to hear.
Yeah, that was probably very confusing to hear. There is a very confusing what do you call it? representation of this online where of this very infamous problem where x equals 0.999 and you're trying to prove that that equals 1. So there's a very common misconception where you can take x as 0.999, multiply 10 on both sides, and then do some operations. No, that's just not how it works, because when you're taking numbers to infinity, you can't just add numbers like that. Like, that's not really how it works. So that's why this very common way of doing it. So if you guys have heard of this problem, you probably know what I'm talking about. It'll probably make more sense to you. But if you have heard of this and have heard of this method of doing it, it's wrong. So don't do that. Use the series. It's a lot smarter, and that's the more correct way. Like, yes, it still equals, but that's just a wrong method of doing it.
Yeah.
I think it confuses a lot of people.
That's right. And so, quick little segue.
Yeah, sorry, a quick little tangent there. Oops.
No, quick little segue to our next set of numbers.
Okay.
What happens when there's a number that exists in the world that you can't describe as
a fraction,
as the quotient of two numbers? What happens? Well, probably the most famous one that you know is pi. And e, and phi as well, the golden ratio. These are called irrational numbers. Quite self-explanatory. They're irrational. What this means is that basically it's a number that has an infinite amount of decimal points, which means you can't just take a number and divide it by another number, because you will always get a finite amount of decimal points.
So one question can be like, how could those numbers even exist in nature, right? Like, how could you even, I think we've spoken about this, like how we can find pi, and how, especially e is just compounding interest. Like, that's what you get when you take the limit to infinity. So the idea behind, it's a live recording. I forgot about that. This is important.
No, so you were talking about finding irrational numbers in nature.
Yes. So in nature, you can't really find them, but you have to find them so then how do you even conceptualize them? So the idea behind irrational numbers is that they're not really numbers that we're trying to find, they're just concepts. And then the number that we find applies to the concept. So pi is used when we're talking about circles, spheres, when we're talking about round things. And pi is used actually with a lot of things.
More than just round things.
More than just round things. Pi is used in a lot of scenarios. But pi wasn't invented with the number in mind. Like, we didn't be like 3.14, this is pi. We got to pi, and then we said that this is the number, can't be explained using numbers. It can't be explained using rational numbers.
Yeah.
So the idea behind irrational numbers wasn't that we were trying to get the number first. What I'm trying to say was that we were trying to get the concept, which led us to the number.
And something that's kind of counterintuitive if you're thinking about irrational numbers, you probably think, okay, if you imagine the number line and you imagine every single rational number on the number line, you probably think that the irrational numbers are kind of peppered in here and there, within the real number line. But turns out, in the vast ocean of irrational numbers, you will find very few rational numbers actually floating around, because it turns out that there are infinitely more irrational numbers than there are rational numbers.
That's pretty insane. I think that's pretty insane.
It is pretty insane.
That's crazy, because rational makes so much more sense because they're infinite numbers.
Yeah.
Right? So wouldn't there be infinite combinations of numbers that we can make? But turns out, nope.
One way you can think about this, imagine pi. Pi has, as I said, an infinite amount of decimal points. Now take one of those decimal points and change it for a different number. That is another irrational number, right? But all you took was one number out of the infinite expansion of pi and changed it and got a different one. Now, just take... So that number that we constructed is already...
Yeah, so there are literally infinite numbers that we can change from 1 to 9, basically, and in the whole thing of pi.
Right, and that's just for pi.
And that's just for pi.
Now
imagine
pi plus 1, pi plus 2.
They're all,
you can add any rational number to pi and it will come out as an irrational number. So, yes, irrational numbers are very important. They're also called transcendental numbers, I'm pretty sure.
Transcendental? I've heard that before.
I'm pretty sure that
I've
just
definitely
means
heard that before.
It's just infinite in, not size, but length, I guess. So yeah, importance, circles,
compounding interest.
Whenever you're talking about exponentials, you are automatically talking about E. And one kind of philosophical question that you can ask is why do like these foundational concepts in math involve these infinite irrational numbers?
That's interesting.
Like why is the radius compared to the diameter whatever of a circle is like you can't write it out. You can't say this is pi and then write it on a piece of paper. You just can't do that.
That's true.
It's like infinity and unthinkable numbers is just baked into the reality of our physical universe, which is...
It's interesting. It could be considered philosophical because I think, it's definitely an interesting thing to talk about.
Yeah.
Like, why are there... that's a very interesting thing. There's equal chance that E didn't have to be irrational. Like, it could have been rational.
It could have.
But, we just have it that
actually,
it's not. Well, again, by the way we define it, yeah, it couldn't. No. I know. But, like, what I'm trying to say is that these numbers need not have to be irrational. But, like, it's interesting that they are. And I think it kind of gives a spice to the universe. It gives a little... not that the universe isn't interesting, but it makes it even a little bit more interesting.
Yeah, and
with these irrational numbers being so important.
And very mysterious.
Yeah.
I was gonna say... I don't know. I forget. Anyways, if all of those numbers weren't enough, 1843 comes around.
Big year.
William Rowan Hamilton was the originator of this number or this set of numbers. It's called the imaginary numbers, the complex numbers. So these numbers aren't taught
it is. I was taught in high school.
I didn't learn them in high school. I knew what they were from YouTube and
I guess
other things like that. But the reason why not everybody knows about imaginary numbers is because they're very mystical and unimaginable, really. You say it's a number that doesn't exist. It was defined, the imaginary numbers were defined because they weren't defined. So we said, you know what, this number doesn't exist, so let's just say it exists. Yeah. We'll assign this value that just can't be found, we'll just assign it to the letter I, and then we'll use it and we'll play around with it and see what happens. Turns out very important. Go ahead.
So what is the value, of I for probably people that, I don't know if you know it, that's awesome. So I is represented as the square root of -1. Now, we don't really know a square root of negative because nothing squared gives us a negative number.
Right, so if you take a positive number, you multiply it by itself, you get a positive number.
Yeah.
If you take a negative number, multiply it by itself, you get a positive number. So if you take a square root of a positive number, right, the original value can be positive or negative, right? Because either way, the negative sign goes away. So if you take the square root of 81, it could be plus or minus 9. But what number times itself
gives you a negative number? What? That's insane.
It's just not, number. By definition, it doesn't exist. It's just not defined. And so what we did is we said, well, not we.
No, I wish we. That would have been cool.
What happened is that they said, okay, let's just take the square root of -1 and call it I.
So I guess the idea basically was like, hey, listen, this doesn't work, so let's invent a system for it. So, because for example, square root of -16, what would that be? If you would know complex numbers, 4i. How would you do that? Factoring out the -1. But the idea of doing that is like, where could it be useful? Where is I useful? So I is useful a lot in engineering, right? I don't actually know how though. Do you know how? Because I'm not in engineering, but I know it's because every time I heard about I, all the teachers are like, it's so useful in engineering and a lot of architecture and stuff like that. And I'm like, okay.
I know it's used in electrical engineering because of the whole e to the pi I thing.
Oh, sorry, not architecture, electrical. That makes more sense.
Electrical
makes more sense. Yeah.
Yes. I was gonna say that if you square I, you get -1. So that's the whole shtick with I.
That's the whole shtick.
Is that when you square it, you get a negative number. So what happens is that when you have, let's say, a Cartesian plane, on the x-axis you have the real numbers, and on the y-axis you have the imaginary numbers. So you write 1 unit in the real numbers is 1, and 1 unit in the imaginary numbers is it's I. It's the square root of -1. And so you can create vectors with these points on that plane. And so just take into consideration the real numbers. If you're looking at a vector in or any amount of dimensions, you can calculate its length by taking the square root of the sum of the squares of each component. And if you don't know what I'm talking about right now, it's just Pythagorean theorem, but you just got to go through the steps to that. It's just a fact. That's how you find the length of a vector.
Okay? Yeah.
But if you're trying to find the length of an imaginary vector or complex vector, let's say it's 1 plus I. So it's got a 45-degree angle, and you're trying to find the length of it. What happens is that when you take...
Have you helped them visualize the plane though?
Yeah,
the x-axis and the y-axis? Okay, yeah. Okay.
So if you're looking for the length, what happens is that if you take the square root of the sum of the squares of the components, right? The second component, when you square it, you will get a negative number. And so what happens is that, I say what happens a lot, but so...
It doesn't actually happen.
Following from this last conclusion, it doesn't work. You can't find the length of a complex vector using Pythagorean theorem. What happens? Not what happens.
Oh my God.
Oh, that's your phone.
Yeah.
Okay,
give me one. Sorry.
Okay.
Yeah.
Brief interruption.
I apologize.
Oh yeah, I was gonna say you need a conjugate. What is a conjugate? Okay, I will let you know. So if you have a real part and an imaginary part to your vector, the conjugate is just negating the imaginary part. So let's say you have 1 plus I. The conjugate is going to be 1 minus I. And what happens, not what happens, I say that too much.
Well, first, let me say one thing. The conjugate doesn't only necessarily apply to complex numbers. It applies to, well, technically anything. Because like A plus B, any A plus B.
Yeah, that's
so the conjugate of two numbers. So if you have a number A and you have a number B, you have A plus B. The conjugate would be A plus B into A minus B. So you're multiplying by the first term, subtracting the second. Why? Because what do you get? A plus B into A minus B equals A squared minus B squared. So basically, it takes that A plus B and it makes it into something simpler. So this is really useful when you have square roots. And usually with the like rational polynomial equation calculations and stuff, you usually multiply and divide by the conjugate and stuff like that to, rationalize it. So that's usually when you use it. So conjugation doesn't only apply in complex numbers, but it's very useful in complex numbers. And he's going to tell you how.
The reason why it's very useful is because, like I said, when you multiply I by itself, you get a negative. But what you're looking for is a positive, because you're looking to add the squares and then take the square root. So if you want to add the squares, you throw a negative sign, right? And that's where the conjugate comes in. You throw a negative sign in front of the second I, and then when you multiply it by itself, the I turns into a -1, and then the negative cancels out the negative, and then it turns out what you're doing is you're just trying to get rid of the I, so you're adding the real part plus just the amount of units of I.
Again, basically you're trying to get rid of that square root, so you're trying to square it is basically what you're trying to do. So a complex number, I think Parker already said, like 1 plus I, for example, has the formula, you can say, of A plus BI. I think we can talk more about this, where A would be one number, B would be another number, I would be the imaginary. So in the case of when Parker said 1 plus I, A was 1 and B was also 1. So it was 1 plus 1I. That was basically the scenario.
Yeah.
So taking 1 plus 1I, and if we multiply that by 1 minus 1I, what we get is A squared minus B squared. So we get 1 minus I squared. But then I squared is just negative 1, right? So then we get 2. Because it's 1 plus 1.
And then square rooted.
And then square rooted.
Which is actually the length of a vector that is 1, 1, 1 in the x and y direction.
Interestingly enough. Yeah.
I was going to say...
you have to square root it. Yeah.
I forgot to say, when we were explaining why I is so weird and mystical, I was going to say a way to envision what I means is imagine a quadratic equation. I'm assuming our listeners know what a quadratic equation is. Like a
parabola,
right?
On a graph.
A parabola.
You know?
So when the parabola intersects the x-axis, you can solve the quadratic equation to find the roots. Now, a quadratic equation usually has either 1 root, 2 roots, or 0 roots.
Just a reminder, quadratic equation, again, if you do not know, it's ax squared plus bx plus c, where x is your dependent variable. A, B, C are just 3 coefficients that you have, and that's your form. That's your formula that you're trying to find x for.
So when your parabola doesn't have any roots, it's because it doesn't intersect the x-axis. It can either be strictly positive or strictly negative. What happened?
Because okay.
No, go ahead.
Again, so what he's trying to say is, imagine like a parabola. If this is your graph, imagine the parabola just here, right?
Yeah.
If it's here, it doesn't intersect the x-axis, or if it's here, it doesn't intersect the x-axis whatsoever. And again, for when I'm saying here, again, for the Spotify listeners, I guess it would be a lot harder to visualize what I'm saying, because it is a video, so I'm kind of assuming that people are going to be on the video. But again, for the Spotify listeners, is just imagine an x-axis and the parabola just concave upwards and over the x-axis. So it just does not intersect it whatsoever.
Yeah. And so when you do the quadratic equation, you might notice that there's a square root in there.
Oh.
And you might notice that when you solve the quadratic equation and you get a negative, right, that when the determinant is negative in the quadratic equation, you stop there and you say no roots.
What is the determinant?
So the determinant are the terms under the square root. So it's b squared minus 4ac.
Yeah. And b, a, c are just your coefficients.
Right, that Ray mentioned earlier.
Yeah.
So now, because we defined I, every single parabola has roots.
Yeah.
Because you can say it's minus b plus or minus I times whatever, right, the positive, or not the positive, but just the number next to I.
Taking out the negative, factoring out the negative.
So every parabola has
roots.
Either 2 real roots, 1 real root, or
one imaginary root or 2 imaginary.
One imaginary root or 2 imaginary roots.
No, they both always have to have 2. So it's either 2 real roots, 1 real root, 1 imaginary,
really?
Because they always have to. It's a parabola. It's quadratic.
But how is there 1 real and 1 imaginary?
Oh yeah, that doesn't even work. That wouldn't even work. That wouldn't even work. Sorry. Oh wait, that wouldn't even work.
No,
they would both be the same.
Because it would be 0. It would be 0 under the square root.
No. If the only way that there can be 1 real is if they're equal. If it hits it like this.
But I'm talking about in the quadratic equation. That's when the determinant is 0, right?
Oh, if the determinant is 0,
right?
Yeah.
So that's not possible. Jesus.
Oh my God, I apologize. Again, this will all be cut out of the audio part.
Cancel?
Yeah, no, I can't. It's a lot of stuff. My grandma has to answer it.
Anyways. Yes, this is what happens when we record live.
Yeah, I'm sorry, we're recording in a house. Like, what do you expect? I apologize to the viewers.
Hello, everybody.
Okay,
so the video actually cut out.
Or sorry.
But yeah. Anyways, I guess you guys didn't have to experience the phone call that we got.
Yeah. So basically, yeah, you would have already heard everything.
Yeah, we're just gonna put a black screen for when it cut out. But yeah, we're back now, hopefully.
Yeah, so, I think we're good.
So I don't even remember what I was talking. Oh yeah, we're talking about roots. So there's either two real, one real, or two imaginary.
Yeah, but again, the one real will be one real when they're equal, right. Or the zero.
Yeah.
Yeah. Okay, that's right. That makes sense.
So the importance of imaginary numbers.
The importance of imaginary numbers.
Quantum mechanics. I don't think we can get into that right now.
Oh, they're so important in quantum mechanics. Okay, so wait. Do we have enough time?
No, we don't. We're almost at 40 minutes.
Why did you bring it up? There's so much to talk about.
We can record quantum mechanics part 2 and talk about.
And then we can talk about imaginary numbers. Okay, well, this is a big suspense because I mean I already know what I want to talk about now.
Yeah.
It's very useful in quantum mechanics because quantum mechanics heavily depends on imaginary numbers. Yeah. Everything is complex.
That's right.
Right. Yeah.
So we are pulling up to almost 40 minutes now.
Yeah. I think it's okay. It was a live recording. Again, for the viewers, we do apologize. I don't really know. I think the video has a cap on how long it records or something. So we're sorry for the black screen or the thumbnail.
Yeah.
We might just put our thumbnail for a bit. So let's see. Yep. That's it.
Thank you for tuning in to our very first live podcast.
Yep.
This was episode 28? 27? Yeah.
Black pen, red pen was 26, right?
Let me just double check.
Yeah, black pen, red pen was 26. Yeah, this is 27. Episode 27. This is episode 27.
So yeah, I hope you guys enjoyed our little discussion on numbers. Yep. I hope you learned something.
We can probably have another one because I think numbers we can also kind of extend into, we can talk about planes. And we can talk about...
Oh, we didn't talk about vectors.
We didn't talk about vectors. We didn't talk about ordered pairs. Yeah. We didn't talk about planes. We can talk about, maybe space-time is a little different. I was thinking of like coordinate systems. Yeah, but we can talk about a lot of things when it comes to numbers.
Definitely.
So yeah, we have a lot to talk about.
So make sure to follow the podcast on Spotify or Apple. Or Google. I think we have like one Google listener.
No, we have a few Google listeners.
Really?
We have 4 to 5% of our listeners are on Google Podcasts.
Okay, well, thank you. Thank you for tuning in.
Thank you.
Leave a comment. Ask some questions. Right, we'll leave our email.
I should say some people have asked questions and we have seen them. I don't want to like disregard them because we haven't replied to all of them. So we have seen the questions. Some of you have asked about pre-calculus videos, or at least the tips and tricks about it and stuff like that. So we have seen them, we have read them, but we may talk about them in a future video. But just you are being recognized. So if you have more questions, just keep shooting them, and if we find something really interesting, we might make a video like on the spot.
So new podcasts every single week. Follow the Instagram. We let you guys know when the episodes are coming out, but they usually come out every single Saturday at 10 a.m. Eastern Standard Time. We also have updates if you want to ask us questions on Spotify. Instagram.
Yeah.
I think this is dragging on a little bit.
A little bit too long, but Instagram is Math and Physics Podcast. Go follow
math.physics.podcast. All right, we're ending it here.
We're ending it. Thank you so much, everyone.
Yes.
Finally saw our faces.
This was the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we will see you soon.
See ya.